Okay, so the idea is when you want to prove forward simulation results in small step style is basically to show that every transition, every reduction in the execution of the source program is simulated by some transitions in the compiled program while preserving some kind of relation or invariant that says, okay, the current state of the machine stays in sync with the term that we are reducing. And the simplest such simulation is what I call the lockstep simulation. So every transition of the source is simulated by exactly one transition in the compiled code. So if the source can go from command C1 state S1 to C2 S2, then the machine and some invariant holds between this and that machine state. Okay. Typically, the variable states will be the same, and the PC will correspond in some way to C1. Then the dashed lines are the conclusions of the diagram. Then the machine can do one transition, and the invariant still holds. So if you can show that, if you can further show that initial states are related, okay, so that's the initial state of the machine when it's executing C. And if you can further show that final states are some quasi-related, so this is a final state for imp, and if it is related to some machine state, then either that machine state is stopped, correctly stopped, or it can do some more reductions and stop cleanly. So if you can do those three things, then you have a preservation of termination and preservation of divergence, because you start in your initial states, which are related by hypothesis. We showed that. Then you do one transition here. We can do the same here. One more transition there. If this terminates normally, eventually we get to skip. And now the machine can do some more transitions and hold with the same store, final store. And so termination here is correctly simulated by termination there. And likewise, if C1 S1 reduces infinitely, so now you have an infinite sequence of transitions in your source, infinite sequence of transitions in your compiled code, and divergence is preserved. So that's the easy case. Sometimes the transitions in the source program are simulated by one or several transitions in the compiled code. An example is assignment for imp, which contains at least one instruction, but often several, to compute the value of A, and then one set variable instruction. So we execute several machine instructions for one transition of imp, of the source code. So now here you put as conclusion that there exist one or several transitions that bring you to a related state, and you can still conclude exactly as before. Okay, that terminating behaviors are preserved and diverging behaviors are preserved too. In yet other cases, sometimes transitions of the source program are simulated by 0, 1, or several transitions in the compiled code. And that's where things get slightly ugly. An example in imp, we have this source reduction, skip followed by C reduces to C. And if you look at the compiled code for skip followed by C, it's exactly the code for C. So the machine is not going to make any progress at that point. Okay, it will just stay in place, and while the source is doing one reduction. So yes, you can write and prove diagrams like this with a star here. So 0, 1, or several transitions. And terminating executions are still preserved, but diverging executions may not be preserved. So let me explain that. It's called the stuttering problem, or infinite stuttering problem, because then it could be the case that we have infinitely many reductions in imp, and for each of those reductions we are not making any progress in the machine. Okay, so the machine basically is stuck at some point, but still our diagram doesn't violate our diagram. So here we have divergence, and here we don't know what's happening. Maybe the machine is crashed already. And, or maybe it has already terminated on some random state, and that's not good. So here is a case where that could happen. Say we optimize our compilation from imp to virtual machine by special casing this infinite loop, while true do skip and gets compiled to no code at all. That's a hell of an optimization, okay? It's like the old joke about the Linux kernel that is so well written it executes all infinite loops in less than 10 seconds. And so we are doing the same thing here. And just for fun, so that loop actually reduces to that, which reduces to this, which reduces to that. So those three terms we are going to compile to no code at all. And well, and if we hack correctly our relation, we can prove a star simulation diagram, okay, that says, well, here we have those three reductions that correspond to no reduction in the compiled code being actually empty. So basically here we have divergence, and here the machine has terminated already. And so what is there to conclude about this stupid optimization? Well, it's a buggy optimization, okay? We don't want it. We want to preserve divergence. But just showing a diagram like this does not rule out such bugs, okay? So we have a buggy compiler, but it satisfies this diagram. So clearly this diagram is not good enough. So let's make it a little better. Oops, sorry. And the idea is to add a measure, for instance, valued over natural numbers, over source terms, so that when we stutter, so when we have a reduction that corresponds to no transition of the virtual machine, then the measure decreases strictly, okay? And however, in the other cases, we have no constraint over the measure. So if we have one reduction that is simulated by at least one transition of the virtual machine, then we don't put any constraint on the measure. And the idea is simple, is that because of that measure, you cannot take infinitely many stuttering steps. At some point, the measure will drop to 0, okay? That case doesn't apply, and you must be in that case, so the machine must make at least one step. And that's enough to show preservation of forward simulation, both for terminating executions and for diverging executions. Okay, so that's kind of, well, maybe not the most general forward simulation diagram, but a fairly general one that can be used for many compilation schemes. Okay, let's put that into practice for our imp2 virtual machine compiler. So let's try to prove a star simulation diagram for our compiler. And oh boy, this is going to be painful because we have two things to do. One is to rule out infinite stuttering, so find that measure that prevents stuttering. And the second will be to relate the current command C and the state of the machine. And as you will see, it's not completely obvious. So first difficulty. So what is a stuttering reduction for imp? Well, it's a reduction from C1 to C2, such that basically the compiled code for C1 is the same as the code for C2. So you're not the machine is not making any progress. Okay, it's going to stay in place. And so here are the main ones, I think. So skip followed by C, reducing to C. As we saw earlier, these two commands have the same code. C1 followed by C, reducing to C2 followed by C if this reduction stutters. Okay. If true, then C1 else C2, because the compiler is so clever that it generated no instruction for the if true, and basically it just gives you the code for C1. And this reduction for while B do C and, reducing to if then else skip. Again, as we will see later, the machine is not making any progress here. It will make progress when B gets tested. All right, so we need a measure M that satisfies at least those 4 inequations, right? Corresponding to those 4 stuttering reductions. And that's where things are going horribly wrong, because let's take my favorite infinite loop, while true do skip and. This measure must be greater than its unrolling, if true then which must be greater than the then branch, which is skip followed by while true which by this rule must be greater than the measure of the original loop. Okay, so no, we can't find any measure that will satisfy all this. So I've scratched my head for a long time on this example, trying to find even more general diagrams that where you would measure not just the command, for instance, but perhaps also some parameters of the machine or whatever. So I'm still scratching my head on that, but there's a cop-out in this situation, which is to change the compilation scheme, okay? And when you're really in trouble with those diagrams, you can add some no operations in the generated code. Yeah, I know. But if you just add this no operation, which is a branch that stays in place, okay, if you just add this no operation at the beginning of the compiled code for any loop, or maybe just for while true loops, actually. I should check that. Anyway, if you just add this no operation, then the machine can execute that no operation when you reduce the while. And so it's no longer a stuttering transition. It's now a transition that does work, even if it's just executing a no operation, okay? And now everything will work much better in the proof because of that. Yes, because if you just rule out this last case, then it's very easy to find such a measure. It's basically the size of the term, okay, size of the command. All right, but that was only problem number one. Problem number two, yes? Well, you can test, of course, and look at the code, or you could have a second pass that is going to remove those no-ops. Because that second pass may have, so it will again be a star simulation diagram, but then maybe there's a more obvious measure, decreasing measure, kind of number of instructions or something like that. So yeah, you could optimize that no-op away after, although it's really unpleasant to have to do that. Okay, problem number two is relating the current command with the compiled code. So remember the big step proof, we had this predicate that just says, okay, at PC, so this is the big code generated for the whole program. And at PC, we have the compiled code for the current command, the command under focus. And in a small step proof, that predicate is not enough because there's what I call the spontaneous generation of commands. So you know the spontaneous generation theory? That's a middle-aged theory that says that flies spontaneously generate from excrement or that kind of things, okay? And here, in those reduction semantics, during reduction, there appears terms that were not in your original program, and terms that the compiler never saw, okay? So terms for which the compiler didn't generate any code. Example, if. So we have an if, then C1 LC2, followed by some code C, that reduces, because B is true, to C1 followed by C. This is the compiled code for this command on the left. So code for B with a test, followed by a code for C1, followed by a branch, followed by a code for C2, followed by the code for C. And then there might be some other code before and after. And this code nowhere contains a compiled code for the right-hand side, C1 followed by C, which is just code for C1, immediately followed by code for C2. Okay, you can't find it here. And the same goes for the unrolling rule for while. Okay, so this I wrote in my original code, so it can be found in the compiled code, but this I never wrote in my original code. Okay. So how are we going to find it in the compiled code, to find its translation, to find an equivalent state in the compiled code? Well, there's a trick, which is to define a non-deterministic relation that generalizes compiled code at. And what does it say? It says that between PC1 and PC2, there's a path of instructions in this compiled code capital C that spells out machine instructions that execute the command C. But those instructions are not necessarily exactly those you get by compiling C, because that relation tolerates the insertion of branches in the middle of the path. Okay, so of unconditional branches in the middle of the path. So I hope I have pictures to explain that. Yes. So for instance, according to this relation, which is defined in the Coq development, compile.v, if you start here at PC1 and end there at PC2, you can spell out the code for C1 followed by C, because indeed here you can spell out the code for C1, and then you can branch to the code for C. Okay, so that's a more tolerant view of the compiled code than really demanding that it contains exactly the code that the compiler would generate. And likewise for a while loop, so here you need to squint. Say we are here just after the conditional test, and now I'm claimed that between this point and that point I have the instructions for C while B do C end. And indeed I have the code for C, and I have a branch that takes me back to the code for while B do C end. And likewise, I didn't show it, but too bad, between this point here, PC0 and PC2, I have the code for while B do C end, of course, but I also have the code for if B, then C followed by while B, if B, then C followed by the loop, else skip. Okay, and so that's how I'm going to tolerate this spontaneous generation of terms. If you squint enough, their code is already present in the compiled code. Okay. Okay, and so in the end, we can finally prove a star simulation diagram. So one transition is the source code. Here, our invariant that says that the machine is really in a state that that matches, sorry, is at a PC1 that corresponds, that contains the code for C1. Then either the machine can do one or several transitions, or it can do 0, 1 or several transitions, and the size of the command decreases. Sorry, I guess that must be greater than or equal. And the invariant is preserved. And so from this diagram, we get forward simulation, and we get preservation of terminating and non-terminating behaviors, all in one proof. Okay. But that's a significantly harder proof than what we did with big step semantics. So I guess that would be my conclusion for today. So we've seen compiler proofs based on those two paradigms, big step and small step semantics. So big step is, well, basically the statements of what needs to be proved is easier to find. Okay, we didn't have to scratch our head too long to find what needs to be proved. The structure of the proof follows the structure of the compiled code. So there's no spontaneous generation or whatever. We're only ever considering subterms of the original program, and that is a nice feature in my opinion. But we have to do separate proofs for termination and divergence. And now if we use small step semantics, we have only one proof, just this simulation diagram that proves both termination and divergence. And in a way, the proof is minimal in terms of number of cases. I'm not quite sure what I wanted to say here, but yeah, well, basically there's exactly one proof case per reduction rule and no more. So you need to invent more complicated invariants between states. You need to invent decreasing measures. Sometimes it's hard. And sometimes you even need, when you're really unlucky, you need to tweak your compilation scheme a little so that the proof will go through. And while I found proofs based on big step semantics slightly more resistant in this respect. Okay, so I think I should stop here for today and just advertise tomorrow's lecture. Tomorrow we do optimizations and static analysis, and that will be fun. Questions? Yes, please.
How robust is this nice correspondence between big steps, co-inductive big step, and small step semantics? Kind of, how does it say to more languages with more features? For example,
well, basically, let's say when you add new features, in general, if you add n rules to the small step semantics, you may have to add n rules two N rules to the big step semantics, basically N for the terminating case and N maybe or maybe not for the diverging case. So again, yeah, there's a little more verbosity in the big step semantics. However, sometimes the big step rules are just easier to write down the first time. Okay.